So, this is my attempt to continue the task in experiment reports that we have to hand over. I'm a master's student in physics, and we have several experiment reports. We did the experiments and we have to hand over the reports of them, and this is one of the last ones that I'm trying to continue and beginning the task for it. So it's about the superconductivity. Since I'm trying to solve the task, I don't get into the introduction of the superconductivities, but just try to go just directly to the task itself. So we have some container. It's better that I draw this. I don't say it in detail, but we have a container like this. We had kind of when we had the experiment, and which we put the liquid nitrogen and liquid helium inside this container, and to make it cool. Here we put the liquid nitrogen, which we brought from a big container, and here there was the liquid helium. So this is nitrogen. This is my first attempt, so maybe this is not very good written. And this is liquid helium. This helps us to bring the temperature of the whatever is inside here to the around 3-4 Kelvin, and that's what we are attempting to do to reach that temperature to be able to reach the superconductivity state. And here we have some coil that we try to get the voltage difference of this one, and we read the voltage difference of the coil and whatever is inside it, and okay, my mouse doesn't work. Okay, so we try to actually we can go to the detail that for example it's actually measuring if this is a coil, it's actually measuring the this is a reference temperature, and this is a coil temperature, and measuring the difference between the voltage of these two. And with this one, with this system, we will get something like this. If this is the voltage, we get the graph that is like this. If this is temperature, this is the difference voltage, we get something around this. That here we will get the superconductivity, and that happens, and also we can measure the yeah the task that we want, which is a transition temperature and transition magnetic field, if I'm not mistaken. But anyhow, for now we want to determine the transition temperature, and we use the metal. The metal here that we use is indium. So this is this is indium, and in the theory we calculated that the transition where is it? Yeah. In the theory, in the report, we calculate that the transition temperature, which we call it Tc for the indium, it's 3.40 Kelvin. So, and I forgot some parts. Okay. Seems we made a mistake, but anyhow. The band gap that we achieved for the theory, which now I don't go into the detail because I should read it again, but the band gap was calculated in this situation with this kind of a formula. This is a Boltzmann constant, and this is a transition temperature. So this band gap that we got would be with this one, if I'm not mistaken. We got it as a 1.02 millielectron volt. And so because I guess this was one part of the task, so the first task that we had is determine the transition temperature for this indium, and which it said that choose your sampling frequency in a proper way in order to be able to follow the transition. I didn't find the paper that we because usually when I go to the experiments I try to write some of the information in the paper, but I didn't find it currently. But maybe I see if I took a note in my computer. So I want to put it on the pause. Can I do it? Yeah. So actually I'm using this streaming to try to kind of force myself to do the report, because I was getting bored and just thinking about doing the report but not doing it. But now I'm using this streaming to continue it, giving me some motivation to do it. Mm-hmm. So what should we do? Maybe it's better that I write it that it would be TC, but a little, if it would be like this. And maybe make it here a little better to understand. And we got the data, different kind of a data for actually the data we got for this temperature transition temperature. We try to, I'm looking at the data now. We got the different kind of different kind of T, and that which is based on a Kelvin, and we measured this difference of the voltage, and because it had a very much fluctuation, we got the average of this the difference of the voltage. So what we got, it was the voltage, millivoltage, and for example it was 3 point something, for example, I don't know, 3.6, which we got 287 millivolts, and we continued until 3.25, which we got it as something like this, but and we get the TC from it, wherever it breaks. But I should do it with the Python, and then we'll show the result if I do the streaming or put a video again. So So for the next task, I should. This is the first task that we have, and for the next one, maybe I just clean this area so I would have a better. I hope it was milli-electron volt. The second task that we have is determine what it is. Yeah, we should calculate the critical magnetic field of the superconductivity. So what did we do? We have the several data. It's not exactly the same as this one. This is For temperature, we have current, which is based on the ampere data that we got. And also we measured the average of voltage as usual, which is, this is millivolt. And this is if this is for each temperature. For example, we got it for a temperature of 299 Kelvin. We also got it for let's see, we got it for 2.7 Kelvin, and the third temperature next one, 2.4 Kelvin, the data that we have. And we have fourth as a 2.1 Kelvin. We measured it several times because it was not always accurate. And we could also, in a theoretical, it should be theoretical. So this is a critical magnetic field. This actually here, when in the first task we didn't have our magnetic field was 0, but we turned on magnetic field for this one by having the current. I guess so. But anyhow, the theory is this one, that it is that is actually has a definition, which is, this is a Sommerfeld coefficient. This is the density of the superconductor, mu 0. smaller mass of superconductor. Continue of it would be temperature, critical temperature. So we get the critical temperature from the first one. Here we do it on the experimental, and we get the critical magnetic field from it, but which for each of the temperature would be different. There is actually in the manual of the report, there is this one. It is a calibration formula that we can transfer the current to the magnetic field. With this is for especially for this setup. So when we have this current, we have the magnetic field. So by the voltage, looking at the sample data, we can see that there would be a graph like similar to the previous one, which this is the difference of the voltage, this is a current which we can get the magnetic field with it. But I guess we would it would be the same as this the other one for here. This is I. We can just transfer it to the B with this calibration formula, and here we can just measure the critical magnetic field. It would be the second exercise. Yeah, the second exercise is set that determine for both sample the critical magnetic field Yeah, but we have here just one sample at 4 temperature, different temperature. Um, hmm. And this would be the second exercise, and kind of the second one, and the second two would be calculating this one, because when we have this one and when we have this one, we can just have a graph of it with this formula, and with the linear regression graph we can measure this value, which would be task 2 1. So yeah, there was theoretical task that I guess we did some part of it, um, for the value of the binding energy, estimation for the value of binding energy and relative distance between two electrons forming a Cooper pair in the superconductivity, and how many other Cooper pairs can be approximately found between the two electrons forming a Cooper pair. Calculate the theoretical value of the thermodynamic critical field BC0 for indium and compare it with the experimental one. Yeah, of course. We can compare it with the last part that we get it from the experimental value. So, better to just do the analyze of this one and then record or stream again. Yeah, that's it. That's a nice abstract of what we have done and what I should do for my next task in this experiment report of the superconductivity. And thank you for watching. Bye.